So here I have a vector math example. I have two vectors, A and B here, and I've drawn them on this coordinate axes down here. So you'll notice, right, they're defined in terms of these two unit vectors, I and J, and sometimes you'll see me write x hat instead of I hat and y hat instead of j hat. And they're just know that they're both the same thing. You can use either of these definitions. It doesn't matter to me. The length is always 1 of every unit vector, and that so in the case of I and j unit vectors, they point along x and y, the x and y axis, and they're usually used to define the components of these other vectors. So let's do the first one. It says express A in terms of its magnitude times its direction. We have a vector A here. To get the magnitude, you just take the square root of the sum of the square of each of the components. So the length of A, which by the way is sometimes just shortened as, we just write A without any vector over the top of it, it's equal to the square root of ax squared plus ay squared. So that would be, plugging in numbers here, in other words, we have root 90 is our length of the vector A. We were asked to express it in terms of a magnitude times a direction. So the direction, then, you can pick out a unit vector that has a length unity and points along a vector that's a hat. So to get a unit vector pointing along a specific vector, all you have to do is take the vector itself and divide by the length of that vector. So it's pretty easy, right? That should make sense to you. If I take a vector which has magnitude and direction, and I divide it by its magnitude, then the length of that vector should be 1. It'll still point in the same direction. So we use a hat to indicate the unit vector that points along the vector A. So I already have the length of A, it's root 90. By any number for any vector, I can just do it on a component by component basis. So this would be the unit vector a hat. So if I wanted to express A, then in terms of its magnitude and its direction, I could write it just like this. The length of A, so its magnitude, times its direction. I'm separating out there the two different aspects of it. So this is a useful thing to write sometimes. So if it's not obvious right away why anybody would want to do this, you'll see as we go along why it's useful to use this notation here. Okay, so this is my answer to part A. So put a box around that, that way whoever's grading my work will know. A and B here are drawn on the coordinate axes, by the way, in these colors that I've circled them over here. And so you can see, right, A, the vector is -9 in its x component and 3 in its j component. So that's the way that it points, right? It points -9 this way, up 3. In the same way, B goes to the right 3 and down 4. Part B, C equals A plus B. Okay, let's find C equals A plus B. Well, there's two different ways that you could find this. So the first thing that you could do is you could take this vector A and you could take this vector B and you could sum them up tip to tail. Okay, so here's what I mean by that. This would be the graphical way to find vector C equals A plus B. I could take B and I I could pick it up and move it. So if I were to do that, I've gone along A, and I've summed along B as well. So my resultant then would be C, this vector that points from the tip of A, or from the tail of A up to the tip of B. This C here is called the resultant. It's what happens after you superimpose two different vectors on top of each other. So that's the graphical way of adding the two together. I can also do it the algebraic way, right, where I add them component by component. So I already have it written down up here, right? It's minus 9I hat plus 3J hat plus these other two terms here. Well, when I add these two together, it's just going to be a component by component addition. So here you can see, let's just make sure that the vectorial and the graphical representation both check out. Well, does this go minus 6 in the x direction and down 1? It certainly does. So C can be, we can take these two vectors graphically, or we can take them algebraically, and you get the exact same thing. Now, in part C, it wants me to find the angle between A plus B and the x-axis. Okay, so that would be this angle right here, theta. All right, well, what I'll just do is I'll take the angle from this, we'll call this, we'll pick out this little angle here, and then we'll just add 180 degrees to it. So we can call this theta prime. Right. So theta prime has, there's a CY component here. There is a CX component there, right? And they're minus 6 and minus 1. So if I wanted to get, so I know then that the tangent of theta prime is going to be equal to opposite over adjacent, right? CY over CX. .5 degrees, and so I need to add then on the 180 because I took the angle from the negative x-axis rather than the x-axis. So that would imply that theta equals 189.5 degrees. Put a box around that. All right, I just want to point something out. So earlier I took this vector b and I just grabbed it and I slid it up over here, and I told you that that was b. And you might be wondering, well, can they both be b? The thing that exists here and the thing that exists over in the original spot? And the answer is yes. So vectors have a magnitude and they have a direction. However, they don't really have a well-defined position. You're supposed to be able to slide them around. So this vector b, even when I move the location over here, its magnitude is the same, its direction is the same, so it's the same vector. Okay, so now let's do part D. So part D asks you to find the vector d, which is 1/3 a minus b. All right, so whenever you multiply a vector by some scalar quantity, you just take that scalar quantity and multiply it to each one of the individual components. So that's simple enough for A. What about when there's a negative sign in front of it? So if you have B and you want to find minus B, all you have to do is just flip it in the opposite direction. So if I flip this thing around, it looks like upside down B. but that's negative b. Negative b has the components minus 3 I hats plus 4 j hats. And I want to take minus b and add it to 1/3 a. So a is negative 9 I hats plus 3 j hats. So 1/3 a is distribute the 1/3 to each component. And I already drew one of those over here. Take this and I can move it, and I add it onto negative b. This will give me a resultant vector that points up from the tip of the original one to the tail of the final one. Here I have basically 1/3 a plus negative b. So if I had done it in the opposite order, it would look a little bit different as I'm doing it, but I could take this minus b and slide it over here, and then I could take this 1/3 a and slide it up over here, and you'll see that I would end up in the same spot. So it's the same vector d equal 1/3 a minus b. That'll be the same as minus b plus 1/3 a. It's probably not a mind blow or anything like that, but it tends to be more tricky when you think about it in the graphical form. Okay, so one more time then, let's just do it the algebraic way. I have so is that what I have? Well, let's see. 6 in the negative x direction, and about 1, 2, 3, 4, 5 up in the y direction. So I can do it vectorially, I can do it algebraically, and I will get the exact same thing.